All right, gang, going to work problems 3 and 4 real quick here. Problem 3 is just that was a gift. Just wanted you to get into G power and play around with a power analysis. What we typically do in stats is we when we're designing our study, we run what's called a priori power analysis. Um, Spoke in church Sunday, and my mom was back there saying, "Doug, slow down. When you try to speak too fast, your words start to go together." So priori. So what you do is you estimate certain things, the effect size that you think you're going to get, which is usually based on previous literature, and you try to come up with the number of subjects that you're going to need to create to come up with a particular power. And that's the only reason I wanted you to do something like this. So, guys, this is just a straightforward G power. Nothing fancy here. No, at least it wasn't intended to be. Let me see if I can get this moved over a little bit. So, first thing is choose a test family. You should know by now that ANOVA is an F test family. Come in and choose a one way. We want a priori, which is the compute the required sample size. If you come there and hover over, you'll see that a large effect is 0.40, which we have put in. Alpha will always be 0.05. And we want to see achieved power of 85%. Number of groups is 3. Gang, all we got to do now is hit calculate. And we can see that we need a total sample size of 72, which for 3 groups would mean that we would need 24 subjects in each group if we have a balanced design. So, guys, that was intended to be super easy. All right, gang, this is going to be the most I guess in-depth problem we've done yet. So what we got apparently is we've got some. We don't have a balanced design here because we have don't have sample sizes equal across instructor A, B, C, and D. This happens a lot in classes, but for obvious reasons. So we want to conduct an appropriate test and report the results in a summary paragraph. Now, this is probably the one where I was most disappointed in the results that I got. And again, I think it's just a balance from two things. I think, first of all, you guys aren't watching the videos like you need to. I think you're waiting till you get the assignment, then you're going through and trying to find something that goes, it's just not the way I teach. We're going to do a little, we're going to build on it, we're going to learn more, we're going to build on it more and more. And, if that's not what you're willing to do, man, you need to drop the class. You really do. I hate to be so blunt, but you got to watch these videos in entirety if you're buying into what I'm trying to teach you here. If you're just going through the motions, then just do whatever you got to do. But anyway, I want to go through the whole shooting match here. So the very first thing I'd have to do is go to Excel and type in my data. And guys, again, keep in mind that when you type this into your .csv format for Excel, that when you read left or right, all of that information on that particular line is for that one particular student. Now we're going to get into more and more and more as we get fancier. Okay, when we get into Manovas and Mankovas and different designs, we're going to get more variables for each particular subject. So, guys, I've got that saved on my desktop. I already have R up and running. So you can see I've already attached it. So the very first thing I would want to do is I like to kind of start things kind of slowly. And I would like to come in with a box plot. And I'd like to look at this across professor. And, you guys said some kind of goofy things. Some of it is completely understandable. Man, you guys, you're still learning, right? So, and I'm very patient with that, as long as you guys are, watching the videos and doing what I ask you to do. But somebody said that they looked at a box plot and they could tell that the mean was higher for, one group compared to another. Guys, you don't get a mean from a box plot. Now, if you have a symmetric distribution, as we have over here in D, where, this line is about equal to that line and the median is in the center of the of the box, you can look at that and pretty much determine you're going to have a symmetric distribution. So the mean and the median will be approximately equal. But that's not even close to the case for instructor A. So what you get, again, from box plot is you get the 5-number summary, the highest, the lowest, Q1, Q3, and the median. But I can get an indication by comparing the medians how the comparison of the means might behave. And it looks like to me that our ANOVA will probably end up being statistically significant because instructor A seems to have gotten the students who have higher math ACT scores, subscores. So it looks like the distributions are closer for B, C, and D. So I don't know what's going to happen here, but I can see. Actually, I do know what's going to happen because I ran this a couple of days ago. But as I sit here speaking it through, I actually forgot what happened. But it looks like to me, instructor A will be something we'll see in a post-hoc analysis. Their scores will be different than probably B, C, and D. But I don't know. We'll find all that out, won't we? Next thing I'd probably want to do is I'd want to look at the descriptive statistics across all groups for all instructors. One way that you can do this is with the by function. Now, we have to get, I believe I got that correct, Pastex. Yeah, so we have to get Pastex, the package, installed. I've already installed it sometime before, so I only have to access the library. But I can come in now and do by and do ACT across professor, and I can use what's called stat DESC. And it's kind of cool because it breaks down in one kind of a one-stop shop, if you will. The NBR value is just the, I think that stands for, having a hard time remembering what NBR, I think it's the N valid cases, and I think N null is actually the number of missing values. I'm pretty sure I'm right on that. NA is actually missing, I don't know what NBR null is. I'll have to look that up. I'm not sure. But I know this is, N is just the our sample size in Professor A. This is our missing data. This is our minimum value or maximum value. Our range, sum, median, mean, standard error. Confidence interval is a little strange the way they present this. This is not actually your confidence interval because you should know by now that your confidence interval has two numbers. Well, this number is actually your margin of error for the confidence interval, in this case the 95% confidence interval. So you would have to take 1.58 and add it to the mean and subtract it to the mean to actually get your confidence interval. Variance, standard deviation, and then your coefficient of variation. So you can see across, as we compare medians, we can see that they correspond to what we saw in the box plot. And you can see that we get a difference in means. So next thing I'd want to do is I'd want to get into checking assumptions. So I would just come into Levine test, and I would do ACT prof, and I would do center equal mean. All right, guys, I got to install a package, don't I? I got to do library car. All right, let's try this again. All right, gang, so what we would see here is, again, the null hypothesis for Levine's test is that the variance for the population for Professor A, the variance for, if we took all of the students for Professor B, Professor C, Professor D, we can't conclude that those variances are different. The next thing I'd want to do is I'd want to come in and do Shapiro test. Now, guys, I can come in and do this. I can do Shapiro test for ACT. And I'm going to see that I get a p-value of 0.14. the null hypothesis for the Shapiro-Wilk is that we are drawing from a distribution that's normal. Now, guys, you got to remember, we deal with samples, and samples are not normally distributed. Normal distribution, that phrase is specific to populations. We are drawing the sample from a larger population, so we make inferences about populations. What does the distribution look like that I'm drawing these ACTs from? Well, the theory, and ACT folks tell me that it's normally distributed. But I'm drawing these scores from a particular university. Are those scores going to form a normal distribution? Well, I can't reject, because my p-value is greater than 0.05, that the scores are coming from a normal distribution. So softening up that language a little bit, we conclude that we are drawing these scores from a normal distribution. Therefore, we can assume normality. But guys, what we want to do in this situation is we don't really care as much about what we call the univariate normality. We want to look at the distributions within each group. And the easiest way to do that is with the bifunction. So we're going to do ACT across professor, and I want to use, again, Shapiro test. Now, what I get here is I get the same kind of thing, but I get what's called a multivariate normality. And again, so we're looking specifically at the scores for Professor A here. This is what we call a W distribution. Don't worry as much about that. But we notice that all of our p-values are greater than 0.05, so we can assume multivariate normality from each of these ACT subscores across professors. So that's what's most important to us there. Well, gang, I've got that done, so I'm going to come in and run my model. And I'm just going to do that with AOV. So I want ACT across professor. And then I'll come in with the summary of my model. Naturally, the first thing I look at is my p-value. My p-value is less than 0.05, so I have a statistically significant result, which tells me without question I need to come in with a post-hoc test. Now, I remember a couple of you got to hear it. I don't really know what happened. I don't know, again, what's going on, if you're not watching all the videos or what. And if you're not, it's just not going to work. But you just stopped here, and you didn't. The problem that we had here was clearly statistically significant. You reported that. But when you get statistical significance for your model, you must follow it up with a post hoc, because you want to see where these differences lie. And probably the, you can run the Tukey if you want. I kind of like the pairwise t-test best. And it's, really easy to run. So first thing we'll do is our Y, which is ACT, across our predictor, which is professor. I want paired to be false. And I want the p-adjust method, is that right? Yeah. To be Bonferroni. Now, what it gives me here, it gives me my p-values, and I can see that the only p-value that I have that's below 0.05 is between Professor A and Professor D. So the statistical significance we have back here in our model is because of this statistically significant difference in mean ACT between Professor A and Professor D. So I can quickly look at ACT across professor just for the mean, and I can see that Professor A just appears to be getting better students than Professor D. Now, I tell you, this could be, we see this happen a lot. Professor D might be teaching in the spring. We see mean ACT scores lower for our developmental math in the spring because we have certain students who are taking the course over. We also see evening classes sometimes have lower ACTs. So in this situation here, I would want to collect more information. It may not be just that Professor D is just getting bad luck. It might have to do with reputation. It might have to do with scheduling. It could have to do with all kinds of things. Now, the next thing that I would want to do is I would want to get into the effect size. And the effect size, let me go back over to this. Our effect size, what we'll do here, for the overall, we'll do what's called the partial eta squared. And the partial eta squared we can find by taking the sum of squares for our model divided by the sum of squares for our model plus the sum of squares for our error. Now what I want you to think about when you see this is think about the r squared that we encounter in regression. And I'll show you something in a second that shows how that actually works. So gang, let's do that. We'll go back to our model and or to our ANOVA output. So eta squared here is going to be my sum of squares for our model, which is 41.06. Divided by 41.06 plus our sum of squares for our error, and that's 56.08. So eta squared is going to be 0.42. Now, that's fine enough, but our focus here is going to be more on individual differences. And the individual difference that has got my attention right now is this difference between A and D. So what I would want to do here is I would want to come in also and calculate the effect size for the difference that I found to be statistically significant. And the way I'll do that is I'll install a package, and I've already installed it, called Compute ES. And this allows me to use what's called MES, and we've talked about this before. And I'll tell you what, I'm going to go back up here and do the by, because I want this stuff right in front of me. Now, what the MES does is I'll take the mean of Professor A, which is 15.67, and the mean of Professor D, which is 12. Then I put in a standard deviation for Professor A, which is 1.51, and I'll put in a standard deviation for Professor B, which is 1.58, and then I'll put in the sample size, which is 6 and 5. And what this will do, it'll give me my effect size D, which is 2.38. And another thing we'll probably want to calculate is R. This is thought to be, another measure of effect size. Now this D tells me in standard errors how different these means are from Professor A and Professor D. So 2 standard errors difference is a very large effect. So I tend to think anything from 0 to 1 is a small effect, anything from 1 to 2 is a moderate effect, and anything from 2 above is a large effect. Okay. All right, gang. Let's go to G power and make some things happen. So we same thing we did before, but we want to come down to a post hoc, see what we achieved as our power, because this is going to let us tap into, if the research is saying that certain things are statistically significant, certain relationships are statistically significant, and we find that ours isn't, well, we want to see if that's really due in part to something that we created in our experimental design, or if we didn't reject the null simply because we didn't have enough power to reject a null if it had been false. So that's ultimately what we're going to carry out here. Okay. So first thing we need to do, I want to show you. See, this has got effect size f, and we calculated the partial eta squared. So I need to come over here, and I want to come down here to direct, and I want to put in partial eta squared of what did we say it was? 0.42. And I want to calculate that. So what that's going to do is it's going to take the partial eta squared and it's going to convert it to the effect size f that G power is using. So I'm going to calculate and transfer this to the main window. Now, if some of you are saying, oh, wait a minute, Darbo, you didn't show us that. You're right. I don't think I did show you this. The only people who I took off on at this stage of the game for effect size and power is if you didn't report anything. As long as you reported something, you got credit for it. It's only the people who just completely, dismissed something, dismissed it completely that lost points. Our total sample size was 21, and we have 3 groups. Now, I'll go ahead and tell you, our G power is going to lose its mind because it wants equal balanced design. So, well, no, actually it didn't. Okay, so wait a minute, that's not right. We had 4 groups, didn't we? Yeah. Yeah. Okay, so it's going to calculate the analysis on average group size, which is okay. Now we look at our power, and our power is 0.84, which is saying that if the null hypothesis is false, then we have a 0.84 probability of rejecting it. So we have adequate power to detect a significant difference if it exists across instructor. Well, gang, now comes the fun part, writing all this stuff up. I've already gone ahead and written it up. The answer to number 3, as we talked about earlier, was 24 per group, 72 total. So the first thing I say a one-way ANOVA was conducted to examine the equality of mean ACT math subscore across instructor. I came in and gave the mean, standard deviation, and sample size. If my sample size had been consistent, if I had a balanced design, I probably would have just left the ends out of this and came in and said we had a balanced design, total sample size of 24, 6 subjects for each instructor. Levine's test of equal variances, I come in and report it, let the reader know that equal variances may be assumed, and then I come in and report the multivariate normality across distributions. Guys, it's very, very important that you report the assumptions of your test. Then I get into the nuts and bolts. I say that there was a significant effect on ACT across levels of instructor. Somebody reading this statement that knows anything about statistics, much at all, will be saying, okay, there's a difference. Now, where is it? So that's why you follow up with a post-hoc. And again, a couple of you didn't even do a post-hoc on a significant ANOVA. And guys, that's just not good. And I don't know why you did that, because every video I talked about ANOVA, I conducted a post-hoc. So I did Bonferroni. You could do Tukey. That's fine. But nevertheless, we saw significant difference between instructor A and D. I came in and report the difference in mean ACT and that the p-value was significant at the 0.5 level. I came in and give the effect size for the overall model. Say that we have adequate power of 0.84. And then I came in and reported the effect size specifically for the comparison of instructor A and D, because that was the difference that was statistically significant. All right, gang, that's it.